All right, let's get started. We're going to be talking about today, we're going to talk about like circuit elements, Ohm's law, and Kirchhoff's laws. But before we get into like those things, let's like quickly go over like things that were discussed like last time. Just make sure like we're all on the same page and do like one quick example to just see how we can actually use it. So if you guys recall, we define I to be the rate of change of charge per unit of time. We define I to be dq dt, and we set the unit for current as amps. We also define like the potential difference of voltage to be the rate that the work is changing per unit of charge, dw dq, and we set the unit for the voltage as volts. We also define power to be the rate that the work is changing per unit of time. So we define it to be dw dt, which we could use chain rule to write it as dw dq times dq dt. We know this guy over here is V, this guy over here is I, so power is V times I, and we know the unit for power is watts, right? So let's just quickly have an example, and let's see like how we can actually like use this thing to solve some problems. Let's just say I'm given a circuit that looks like this. Let's just call this like my element 1. Voltage across it is 12 volts. Current through it is Ix. I have another element here. Let's just call it element 4 with voltage across 24 and current through 2 times Ix, where Ix is this guy over here. I have element 2 with voltage across 8 volts. I have element 3 with voltage across 16 volts. And let's just say the current here is going this direction, and the value for it is 2 amps. And the question is asking us, what is the power absorbed by element? Well, we know the power is VI, so power absorbed by element 1 is 12 times I of X. But the issue here is that we don't really know I of X, so we got to be able to like compute this I of X. So to be able to do that, let's just take a step back and find all the powers that we can have. So if I want to find power for element 1, that is VI, which is 12 times I of X. And we know this is absorbed. So the sign here is positive. P for element 2, again, is VI. But if you look at this I is hitting negative sign. So I have minus 8 times 2. So it's minus 16 watts, which basically means it is supplying. For P3, again, it's the same story. The current is hitting the negative sign first. So it is minus 16 times 2. So it's minus 32 watts. Or in other words, it is 32 watts supplied. Right? How about P for element 4? That is VI. I through it is 2 times Ix. It's hitting positive sign first. So it's 24 times 2Ix, which is 48 I of X. And we know it's absorbed. And for this element over here, let's just call it P36. It is minus 36 times Ix. So it's minus 36 Ix watts, right? Or we can just say it's 36 Ix supplied. So the question here is like, how can we use like these powers to find I of X? Well, what we do know is that we cannot generate power. So power absorbed must be the exact same as power supplied. In other words, if I add up all the powers, it should add up to zero. So if I do that, if I use basically this formula, so I have all the absorbed, so I have 12 times Ix plus P4, which is 48 Ix. That should be the same as all the power supplied, which is 16 plus 32 plus 36ix. Well, this is a very simple like equation. I can basically take this element on this side and solve for I of x. It turns out I of x is 2m. Now I have I of x, I can compute P1. I know P1 here is 12 times I of x, so it's 12 times 2, so it's 24 watts. And since the sign here is positive, it means it's absorbing, right? One thing that we have to pay close attention to is like these signs. So if basically current is hitting the negative sign, the power is basically supplying. And if it's hitting like the positive sign, the power is absorbing. Now we got that out of the way, let's talk about circuit elements. In general, we have two types of elements. We have passive elements and we have active elements. Passive elements are those elements that can not generate energy. So these elements cannot generate energy. The example for them is just basically resistors, capacitors, inductors, and so on and so forth. Active elements, on the other hand, can generate energy. So these elements can generate energies. An example for them is just like voltage or like current sources, right? When we're talking about like sources, we're basically talking about two types of like sources. So kinds of sources. We have two types of like sources. The first type is independent sources. Independent sources are the sources that its values do not depend on anything else in the circuit. So these sources do not depend on other voltages or currents in the circuit. In other words, these elements, the value for them is just about a number or something that changes with time. But their value does not depend on anything else in the circuit. We usually show them with a little circuit. And if you have like a voltage source, independent voltage source, we show them with this. Let's just called the value VT. And if we have an independent current source, we show it with this. The value is basically I of t. Again, it can depend on time, but uh, the value cannot depend on any other like voltage or current in the circuit, right? A very simple example of it is when V of t is a number, for example, 5 volts, or like I of t is like 2 amps, right? So the value does not depend on time. Another kind of sources are dependent sources. Dependent sources are basically an element in the circuit that its value depends on another voltage or current in the circuit. So the magnitude of these elements depend on another voltage or current in the circuit. In general, we have 4 types of dependent sources. So types of dependent sources. The first type, the first type is voltage controlled voltage sources. What it means is that like we have a voltage source. We usually use like diamonds. And the value of like this voltage source depends on another voltage in the circuit. So this is our circuit. And let's just say, like, for example, this is V of S. The value of this voltage source over here depends on this V of S, right? That is voltage constant. Another type is current controlled voltage sources, which is basically a dependent voltage source that its value is being controlled by a current somewhere in the circuit. So if I have like this circuit over here, let's just say like this is current through it, let's just call it I of S. And if this is my voltage source here, the value of voltage here is some number times I of S. So this I of S is controlling voltage across this element. Another type is voltage controlled current source. And as you can guess, it's basically like a dependent current source that its value is being controlled by some voltage in the circuit. So if I have, this is my circuit, let's just say this is some voltage in the circuit, let's just call it V of S. I have a dependent current source where its value I is some constant times this voltage here, right? So as you can see, like the value here depends on some other value in the circuit. In this case, it's just the voltage. And the last type is current controlled current source, which again, it means like I have some current, let's just call it I of S in the circuit, that the value of this dependent source, I, depends on this I of S, right? So these are basically the only types of like dependent sources that we have. Now we have like dependent sources, we have like independent sources. Let's quickly talk about like one of the most important like passive elements that we're dealing with in this course a lot. So passive elements. So the very, very first passive element that we're going to deal with is a resistance. We're going to talk about capacitors and inductors later in this course, but for now, let's just only like focus on like resistors. Resistors are basically elements that do not let the current flow. So elements in the circuit that impede current, right? We usually show like resistors by R. We show resistors by R, and the unit for it is ohms, right? Sometimes we're interested in the inverse of like this value. We define that to be G, which is the inverse of R, and we call this conductance. And the value, the measure that we have for this, the unit for conductance is Siemens. We show it by S. Okay? It's nothing but basically like the inverse of R, right? And oftentimes like a resistor basically uh, dissipates electrical energy, usually through heat, right? But here's a very important thing. If I have like a resistance, which we usually show it in a circuit by something like this resistance will have some current going through it. Let's just call it I. And it has like some voltage across it. Let's just call it V. So we gotta know the relationship between like these three basically items. So we need to know the relationship between V, R, and I. It turns out, it turns out, current through a resistance, a resistor, or in general, any conductor, is directly proportional to the potential difference or voltage and inversely proportional to the resistance. Basically, if I have I is proportional to V. I is also proportional to 1 over R. And it turns out I can make this an equality by looking at this. This formula over here is known as Ohm's law. I can rewrite this and I can write it as V equals R. So let's just like go over this like one more time. So if I have a resistance, let's just say this is my circuit, and this circuit is connected to like a resistance. Let's just call that resistance R. Let's just say voltage across it is V, current through it is I, then V equals R, right? And this is called Ohm's law. If you guys recall, we know V equals Ri. We also know power is equal VI. So if I plug this V in here, what do I get? I get Ri times I. So it turns out P is R times I squared. Again, remember this formula only is true for a resistance, right? This is a very general formula, but this one is only true for a resistance. We can also like replace I by Ohm's law. So if I do that, I have V times V over R. So I have V squared over. So this is like another formula for the power. Remember, remark, P equals VI is a general formula and is true for all elements if we have a resistor with value R, P can also be computed using P equals Ri squared equals V squared over, right? These two formulas are only true for a resistance, right? So let's do a few examples to see like how it works. Example one. Let's just say I have a circuit that looks like this. This is 5 volts. There is a resistance here with value 5 ohms. And the question is, what is this current? Well, we know voltage across this 5 ohms is 5 volts. So we know I is V over R, which is 5 volts divided by 5 ohms, which is 1 amp. Right? Very simple. Let's do another example. Let's just say I have a voltage here. I know the current here is 5 milliamps. And I have a 5 kilo ohms resistance. And the question is, what is V? Again, we know V is Ri. So it's 5K times 5 milliamps. So it is 5 times 10 to the power 3 times 5 times 10 to the minus 3. So it's 25 volts. Again, remember, this is what we have. If we have R, if this is I, if this is V, the relationship here is V equals Ri. Right? Let's do another example. Let's just say I have a circuit. It's just my circuit. And I have I here that is connected to nothing. And the question is like, what is I? Well, I know V over R, that would give me this I. But since this is open and there's nothing over there, it means my R is actually infinity. So it's V over infinity, and we know V over infinity is actually zero. This is called open circuit. So whenever we're talking about open circuit, what it means is that like we have infinite resistance, and therefore there is no current passing through it, right? Let's do another example. Example 4. Let's just say I have a wire here, and then this is connected to the rest of my circuit. And the question here is, what is V of a wire? I know V equals Ri, but since there is no resistance here, R is 0, so it's 0 times I, so it's 0. This is called short circuit. So whenever we're talking about a short circuit, what we mean is that there is no resistance there, the resistor is 0, and therefore the voltage drop or voltage there is actually 0. Right? Very, very simple. But now we know Ohm's law. We basically know like the relationship between V, I, and R. But what if my circuit is a little bit like more complicated? How can I solve that circuit? That brings us basically to Kirchhoff's law. Kirchhoff's laws. There are two kinds of like Kirchhoff's laws. One, Kirchhoff's current law, or KCL. And the second type is Kirchhoff's voltage law, also known as KVL. So let's talk about them a little bit more in detail. So let's start off by Kirchhoff's current law. Kirchhoff's current. What this law is telling us is that if I have a node in a circuit, the currents going in to that node should be the exact same as the currents going out. So what states is that current going in should be the same as current going out, right? I can basically rewrite this and like have everything on one side and put that equal to like 0. So another way of like saying this is equivalent of saying the algebraic sum of all currents going into a node is 0. Again, I kept saying like node, 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 but I haven't defined a node. A node is nothing but a portion of wire that connects a bunch of elements, right? For example, if I have this one, this one, this one, this one. This right here is a node because it connects this element to this element. This right here is like another node because it connects this element to this element, right? And what KCL tells us, or Kirchhoff's current law tells us, is that if I consider any node in the circuit, the current that's going in should be this exact same as the current that's going out. Or equivalently, if I look at the algebraic sum of all the currents going into a node, that should be zero. So let's just have like a quick convention about like this algebraic sum. So this is our convention. If we're entering a node, let's just assume the current is positive. And if we're exiting a node, let's just say the current is negative. And with this convention, let's just say this is one node that I have. Let's just say this is going in, this is going in, this is going out, this is going out, this is going in. Let's just call this I1, I2, I4, I3, and I5. All the currents that are going in, they're positive, and all the currents that are going out, according to our convention, they're negative. Or we can just say like whatever that goes in should be the same as whatever that's coming out. So let's go with whatever that goes in. So it's I1 plus I2 plus I4, which we know that's exactly the same as whatever that goes out, which is I3 plus I5. In another way, we could actually like take these two over here and write it I1 plus I2 plus I4 minus I3 minus I5. That equals to zero. Again, this is our convention. If you want, you can just assume like the reverse. If you're entering a node, that's negative. If you're exiting, that's positive. It's not going to change anything because all it does is that like we have to like multiply like both sides of this equation by a negative sign, which doesn't do anything. It just basically like reverses everything. So it doesn't really matter, right? All we need to like keep in mind is that like whatever current that's going in is exactly the same as the current that's going out. Okay? Let's just do like a quick example and see how it works. Let's just say I'm given this circuit. I have three elements here, which I already know like this current here is 10 milliamps. This current here is 40 milliamps. And this current here is 20 milliamps. And the question is, what is this I? Again, this is my node. What I have down here is my node because that's a portion of circuit that connects a bunch of elements, right? And if I look at this and say, okay, how about like these two? Are they like different nodes? The answer is no, because there's no potential difference between like these two things. So I can rewrite the whole circuit here as something like this, right? And they all can meet at like this one point and nothing gets changed, right? So the whole thing down here is like one node. And we know whatever that goes in should come out. So this I over here is actually coming out. So I is equal to whatever that's going in. So these three I's are going in. So it's 10 milliamps plus 40 milliamps plus 20 milliamps, which is 70, right? Very, very simple. Let's do one more example. let's just say I'm given this circuit. Let's just say the value of here is 2 times I of x. So it's the dependent source, that its value is being controlled by some current in the circuit. So I have to tell you like exactly what that element is. Let's just say the current here is 4 milliamps. Let's just say I have a independent current source with value 12 millivolts. I have I of x over here. And I have like another dependent source with the value 3ix. And the question is asking me what is ix? Well, we know KCL, so we have to like determine like where the node is. So we're gonna look at like the whole thing down here as like one node. Again, because it's the portion of wire that's connecting all these elements, and there is no other element in between, right? So if I look at that as like one node, I know whatever going in should be the exact same thing as whatever that's coming out. So let's just see like whatever's going in. Well, 4 milliamps is going in. I of x is going in. This 3I of x over here is also going in. That should be the exact same as whatever is that's going out. So I have this 12 milliamps right here that's going out. And I have like this 2 times I of x that's going out. This is like very simple equation. So I have 4 times I of x over here. I can bring this thing down here and move this thing over here. What I have is 2 times I of x is 8 milliamps, and therefore I of x is 4 milliamps. Right? So the whole idea here is that we have to like determine like nodes and then write a KCL at that node. Another type of Kirchhoff law is Kirchhoff's voltage law, or KVL. And what it says is pretty much similar to the Kirchhoff current law. But this time, instead of like writing it for a node, we're writing it for loops. And what it says is that if I add up all the voltages in a closed loop, it should add up to 0. So sum of all voltages in a closed loop should be 0. Right? And let's just have like the convention here. And the convention here is that if I have an element and the voltage that we're encountering is going from positive to negative, we're considering that voltage to be positive. Voltage encountered positive to negative, then we consider that voltage to be positive. Voltage encountered from negative to positive, then we're going to think of that as like negative. So if I have basically a circuit, let's just say it has 3 elements. Let's just call this V1. Let's just call this V2. And this one over here, V3. So this is a closed loop. So if I write the KVL, let's just start from here and then go through like this loop. So if I do this, when I get here, I see the first sign, which is positive. So I have plus V1. Over here for the V2, if I basically like travel here, The first sign I see is negative, so I have negative V2. Over here for V3, going that direction, it is positive, so that's going to be V3. And according to KVL, we know it should be 0. One of you guys might ask, why did you take like the clockwise direction? Can I take like counterclockwise? Absolutely. Let's do that. Let's just assume this is the direction that we chose. If this is the direction that we choose, if we're over here, the first sign that we see is negative, so I have negative V1. If I get to like this, the third element here, again, the sign I have here is negative, so it's negative V3. For V2, the first sign I encounter is positive, so it's going to be plus V2, and that is 0. If I multiply both sides of this equation by a negative, what I have is V1 minus V2 plus V3 equals 0, which is exactly the same as this guy. So what's important here is to stick to this convention, but it does not really matter like what direction we're choosing. We can choose clockwise or counterclockwise. As long as we're sticking to this convention, we should be fine, and there's nothing to worry about. Let's just do like a quick example to see exactly like what's happening over here. Example. Let's just say I am given this circuit. This is 6 volts. This is 24 volts. This is 4 volts. This is 6 volts. This is 12 volts. And this is 8 volts. And let's just call this point over here A, over here B, this is C, this is D, this is E, and this is F. One of you guys might ask me, like, how do we know this is negative, this is positive? This is given to you in the problem. So let's just stick to that and just say this is given to us, right? Um, so the very, very first step is to verify KVL. Let's just say we're taking this clockwise direction. Let's just see if the KVL actually verifies, if it's true. And if I add up all the voltages, it adds up to 0. Well, let's just stick to the convention. If we hit positive, the value is positive. If we hit negative, the value is negative. So let's start from here, this voltage source here. So I have 24. As soon as I hit B, I have like a negative sign over there. So I have minus 4. Then I have plus 6 volts because at C, I'm seeing like this positive sign first. Then if I move on to D, I have like minus 12 volts. At E again, I hit negative sign first. I have minus 8. And at F, again, I see negative 6. And if I basically add them all up, this and this is 30. This and this is like minus 20. And this is minus 10. Like the whole thing will add up to 0. So KVL actually checks out. So this is the first part. The second part of the question is asking us, what is V between A and D? Well, if you look at V between like A and D, it's not exactly like a closed loop, but what we can think of is that like there is a voltage here between these two that's called like VAD. So I can still like write the KVL and write VAD equals 24 minus 4 plus 6, and that's it. Because I started from A, I had this like plus, I had this negative, and then I had this like plus over there. So if I add them up, it's basically 26 volts, right? How about VDF? what is VDF? Basically, what is voltage from this point over here up to like this point? Again, this is not exactly like a closed loop, but we can actually think of this as like there is something here that's called VDF. And starting from here, I have VDF equals minus 12 minus 8, which is minus 20, right? So again, this is like very simple, but I would like for you guys to like think about like the differences. For the KCL, we know the currents going into a node is exactly the same as the current that's going out of that node. For the KVL, what it says is that if I have like voltages in a closed loop, and if I add them all up with the signs they have, it should add up to 0. Okay? Let's do a few more examples. Example. Let's just make it a little bit like more interesting and see like how it works. So let's just say I'm given like this circuit. This is 12 milliamps. I have these. I have this guy. And I have like a voltage source here. I have a resistance there, another resistance, and a current source with value 4 milliamps. Let's just call this I of X. Let's just assume here we have a 3 milliamps current going through here. Let's just call this I of Y. Let's just say this is 2 milliamps. Oh, let's just call this I of X. Right? And the question is like, what is IX? What is IY? And what is, let's just call this IZ. IZ. Right? Again, we're asked to find I's. So the best thing that we can do is to use KCL. So let's just call this over here node 1. Let's just call this thing down here node 2. And this thing over here node 3. If I write a KCL at node 1, what do I have? I know whatever current that's going in should be the exact same as the current that's going out. So I have like this 12 millivolts going in, and I have the 3 milliamps and I of X going out. Therefore, I of X is 9 milliamps. How about if I wrote a KCL at node 2? What do I have? Again, whatever current that's going in should be the same as the current that's going out. So 2 milliamps it's going out is the same as 4 milliamps going in plus IZ. Therefore, IZ is negative 2 milliamps. By the way, this negative actually means like the direction that I chose over here is not the correct direction, and the direction is indeed upwards. Basically to get the positive value, right? How about if we wrote the KCL at node 3? What do we have? Again, the current that's going in should be the same as the current that's going out. IY plus IZ plus 12, they're going out. That should be the same as the current that's going in, which is nothing, right? But we already know this IZ is like minus 2. Therefore, I of Y is negative 10 milliamps. right? So it's very, very simple. We can basically obtain all i's just by writing KCl.